So I don't think we had started with hydrodynamics in the last lecture. We had just more or less completed questions of hydrostatics, right? So let's take it from that point onwards. So any doubts pending in hydrostatics, people? I think we had gone through few of the questions from H.C. Verma last time, and then we also discussed about the more tricky situation of buoyant force in non-inertial frame. And finally, we discussed about the paraboloid surface when a liquid is in a rotating container. So that kind of situation. Okay, so let's maybe start with one quick review question of rotating tanks, because that was the last thing we discussed last time. Okay. Fluid mechanics is fairly straightforward and simple chapter in that sense. So you can at this stage just rely on H.C. Verma also for your questions, or if you do H.C. Verma plus your module, it is more than enough. Okay. So anyway, let's look at a quick example. So we have this kind of situation we've seen before. Okay, U-tube kind of thing. Okay, now what we're doing is we are rotating this U-tube about an axis like this, a vertical axis, which is asymmetric with respect to the base of the U-tube. It's rotating at an angular speed omega like this, such that this is 4L by 5. This is L by 5. Okay. And as a result of that, there is a difference in the level of water. These two. So if this height is H2, this height is H1. Okay. So given that L is equal to 100 centimeters, H2 is equal to 60 centimeters, H1 is equal to 40 centimeters, and G is equal to 10 meters per second square. We have to find the angular speed omega naught. Okay, because this is being rotated about a vertical axis as shown at a uniform angular speed. Okay, and the fluid is of course water, so it has that standard density 1 gram per cc. So just try out this question, people. Numerically, we'll discuss soon. So you have to apply the concept of radial pressure gradient, and from that you have to understand the pressure difference between the two corner points. Okay, so if you take the point on the axis as, let's say, A, the point at this corner as B, and the point at the same horizontal level on this side as C. So you can see that radial pressure gradient del P by del R is rho into omega naught square R, where this is your radial axis. Take a radial axis like this or like this on either side of the axis. So when you are calculating the pressure difference between B and A, for example, PB minus PA will be del P by del R integrated over R equal to 0 to R equal to 4L by 5. So pressure at the point B will become pressure at the point A plus rho into omega square to 4L by 5 whole square by 2, or 8 by 25. Okay, and similarly, pressure at C compared to the pressure at A. Okay. So from this, you should be able to get the pressure difference between these two, PC minus or PB minus PC, in terms of the angular speed. That's this. Now using the vertical pressure gradient, take this as your vertical axis. So using that relation, you can see here that pressure at B will be atmospheric pressure plus rho g H1. So from these, you can see that again, the same pressure difference in terms of the vertical gradient, and therefore the height differences, the liquid columns above is this. So now you have to relate this equation with this relation, and we'll get omega from this. So this is the general method of solving it. Okay. Yes, Naman, I'll just check the answer numerically for you, but if you use the same method. So interestingly, we did not even need the value of the density of water, right? So in other words, if we rotate this with a certain omega, the height difference between the two columns will be independent of what liquid is used. The density of the liquid will not play a role. Fifteen by 50, is it?
Yes, sir.
Sorry, yes. Should be 15 by 50, or that is 0.3, 3 by 10. Okay, so that's the relationship here. So omega naught will become square root of 10 by 3 g into this height difference divided by L square. So the height difference was, I think, 20 centimeters, right? 0.2 divided by L was 100 centimeters or 1 meter. So okay, so people hope this question is clear. Now, what we'll do is with this, we more or less finish all the various types of questions in hydrostatics. So let's move on to the theory part of hydrodynamics and complete the theory part of this chapter. And then when we are looking into questions and discussions of hydrodynamics questions, if any more doubts are pending from hydrostatics, we will look at them together. So we'll see the whole chapter, that is hydrostatics plus hydrodynamics doubts together in the end. Okay. So by next week, like, just keep the doubts prepared from the module or anywhere else for hydrostatics as well as hydrodynamics. So hydrodynamics, as the name suggests, it's the physics of a moving fluid. Dynamics is a reference to motion, and hydro is a reference to fluid. Okay. But in this particular chapter, hydrodynamics, we are going to study a very specific type of motion. We're going to study the physics of an ideal fluid in what is called steady flow, or also another name for it is streamline motion or streamline flow. So let's understand the definition of this. So ideal fluid we've already seen before. Ideal fluid is a fluid which has two important properties. It is incompressible, okay, and non-viscous. So incompressible means it has a uniform density, okay, which is independent of pressure. And non-viscous means the coefficient of viscosity is tending to 0. So that also means that there is no non-conservative drag forces. Just a moment, people are joining. Right. So non-viscous means the coefficient of viscosity is something we'll study about in more detail in the next chapter, properties of matter. But that is zero. So there are no non-conservative drag forces within the liquid because of any kind of relative motion. Now let's come to the term steady flow or streamline motion. Now this is a particular type of flow such that a volume element of the fluid has a motion which is both non-turbulent and irrotational. Okay, so irrotational is self-explanatory. It means that if you look at any volume element or mass element or whatever, a delta V or a delta M section of the fluid while it is flowing, it is not undergoing any rotational motion about its own axis. It's undergoing pure translation. But what is the meaning of the term non-turbulent? Okay, so turbulence is sudden and extreme changes in pressure within a fluid and when we say fluid we include non-ideal fluids also. Okay, so that the property of turbulence is when there are sudden and extreme changes in pressure within a fluid due to strong impulses from random and high velocity collisions. So for example, so we'll come to non-turbulence, but what does the term turbulence mean? Turbulence means that if a fluid is flowing in such a way that the fluid elements or the volume elements of fluid undergo high velocity and random collisions, and these collisions involve strong collision impulses, then because of those large magnitude collision impulses acting randomly and suddenly at various points during the fluid, because those fluid elements are making random and high velocity collisions. So those strong collision impulses will create sudden and extreme changes in pressure within the fluid. So when that happens, we say that there is turbulence in the flow. Okay. So an example of extreme turbulence is the motion of water in a rapid waterfall. So rapid waterfall involves both high velocity plus random and you can say high impulse collisions. Okay. Collisions of fluid elements with rocks, etc., or with each other. Both types of collisions occur in such a way that they are high velocity and random collisions. So that creates extreme turbulence. These collisions creates turbulence. So in the case of steady flow, we don't want turbulence. So there should be no sudden changes in pressure inside the fluid as it is in flow, because the fluid flow is not happening in such a way that there will be any random and sudden collisions of high impulse. Some amount of collisions will of course happen, because unless the fluid is moving in uniform straight line motion, which is a very rare case, some amount of collisions will happen because there will be change in direction or change in magnitude of velocity vector for the different fluid elements, but they should be a gradual process. So the collision should not be random and high velocity collisions involving very large value of collision impulses, because those kind of random sudden impulses which are of high magnitude, they create extreme and sudden changes in pressure, and that creates the property of turbulence. So what turbulence does is it makes the prediction, it makes it very difficult to predict the parameters of the fluid while it is in flow, like the kinetic energy per unit volume or the pressure, etc. It makes it very the changes in pressure and the changes in density, etc., in such a fluid will become very extreme and will become very random. So it makes it very difficult to predict any of the parameters related with the motion of the fluid. And hence, it doesn't come in the category of steady flow, because steady flow or streamlined motion is above all, it's a very predictable type of motion where, nothing is changing randomly and nothing is changing suddenly. It's a very ordered and predictable type of flow of a fluid. So it goes completely against the property of turbulence. The moment there is turbulence, it will break that predictability of the flow. It will make it highly random and unpredictable. Okay, so therefore, turbulence is something that we don't want when we are trying to create the situation of steady flow. We want to avoid turbulence altogether so that there are no random and sudden changes in pressure, density, etc., while the fluid is in flow. And of course, we are talking about an ideal fluid. So in any case, the density should not change. So anything that creates sudden and random high value impulses will also create sudden changes in pressure, because of extreme compression that occurs at the point where such collisions occur. So that will break even the property of the fluid being ideal. So turbulence is something that is altogether against the property of steady flow. So that rapid waterfall situation is a good example to visualize turbulence. If you visualize, volume elements of fluid as they are moving along that waterfall, their motion is in no way predictable. Okay. Another example of turbulence, extreme kind of turbulence, is smoke coming out of a chimney at high pressure. Not the kind of, where smoke is coming out gently at a lesser rate, but the kind of situation where you have, let's say, smoke coming out of a chimney in an industrial or a chemical plant at high density. So because of the high density and high pressure, at the point at which the smoke is leaving the chimney, as the smoke comes out, the motion is very unpredictable. And of course, the smoke itself is a highly compressible fluid. It's a gaseous fluid which has very high compressibility. So it is in no way an ideal fluid. The extreme turbulence in it. For that matter, airflow in a situation where there's a cyclone, or at least there is extreme pressure changes because of thunderstorm, etc. So that creates turbulence. So when we say non-turbulent, it is the opposite of that. Okay. So that means the flow of the fluid should be in such a way that there are no sudden changes in pressure. There are no sudden and random changes in pressure at any point inside the fluid. And there are no random high velocity collisions that the fluid elements are undergoing during the flow. The motion should be in a way which is highly predictable and without any random and sudden collisions. So now one way to describe non-turbulent flow is that it is the flow of an ideal fluid such that the pressure gradient within the fluid, that is rate of change of pressure with respect to position. So that pressure gradient within the fluid is comparatively gentle. In other words, there is no sudden and extreme change in pressure at any point within the fluid. So this will only happen when the motion does not involve any high velocity and random collisions. So the motion should not involve random and high velocity collisions for fluid elements. By element of a fluid, we mean a differential element of volume or mass. Like a dm mass or a dv volume of fluid as it is flowing, it should not undergo these kind of collisions. So that will prevent a situation where there is rapid and sudden change in pressure. And irrotational is, as the name suggests, fluid elements should move in such a way that their motion is purely translational. There is no rotation about their own axis happening. So when we put together these two properties of streamline motion, that it is non-turbulent and irrotational. So given that the liquid we are talking about, the fluid we are talking about is an ideal fluid, so there's no viscosity within it and it is incompressible, then that brings out another important aspect of streamline motion. Or steady flow, or you can say that it shows another important property of this type of motion, and that property is that, for example, if this is a visual representation of steady flow of a fluid moving like this, then at any cross section, the velocity of every fluid element passing through that will be uniform. So at a given cross section, the velocity of all fluid elements will be uniform. So what we mean by fluid element, as we discussed before, is a differential volume or mass element. So at a given cross section, all the fluid elements that are crossing through will have the same value of velocity, both in terms of magnitude and direction. So velocity vector of all fluid elements passing through a given cross section will be uniform. Now the next thing is that at any given point in the fluid flow, okay, if a fluid element which is present over here, let's say dm, is having a velocity v at this particular instant of time, then at a later instant of time, this same point is occupied by another particle. So this particle has moved down ahead and the particle behind it has come and occupied that point P. So the new particle or the new fluid element that occupies that position will have the same velocity as the previous one which occupied that position. Okay. So at any point, the velocity vector of a fluid element located at the point at the given instant of time is identical to that of an element located there at an instant before or after. So in plain language, what this means is that every cross section of the fluid has a fixed amount of velocity. So at any instant of time, any fluid element that is passing through that cross section will have that fixed value of velocity. So from cross section to cross section, the velocity profile is a fixed profile. So what this means to say is that if we compare two cross sections within the fluid, one cross section over here, so every fluid particle going through this at a given instant has a velocity v1, and we then compare another cross section somewhere else, and every fluid particle going through this second cross section has a velocity v2. So now you think of a stream of particles as they are going through this section, first crossing this one where the velocity is v1, and then after some time crossing this one where the velocity is v2. So every particle following each other will follow the same velocity profile. Every particle in this stream that is coming one after the other consecutively. As it goes through this cross section, the first one, it will have a velocity v1. Then the next one coming through that cross section will also have that same velocity v1. By the time one particle reaches here, its velocity has changed from v1 to v2. Now the next consecutive one, or the next consecutive one after that, they will also have that same profile. As they cross this point, they will have velocity v1. As they cross this point, they'll have velocity v2. Okay, so fluid elements move with a constant, or you can say steady, velocity profile. So what do we mean by velocity profile is that the velocity at every cross section is a fixed value for any particle passing through at any point of time. It's fixed for all particles passing through at all times. That is what we mean by saying there's a fixed velocity profile. Or a steady velocity profile. So now to these 2 points that we made over here, if you add the fact that the motion of the fluid elements is irrotational, that is, they don't undergo rotations, and it is also non-turbulent. That means they don't violently collide with each other as they are moving. So these 2 points added to this will tell you the fact that the fluid elements move in well-defined paths. Okay, well-defined trajectories of paths which do not cross each other because there's no collision involved. Okay, and these mean by well-defined paths or trajectories is that these trajectories don't change with time. So if we are tracing a fluid element over here at some instant of time, it is following this path which I've shown with the violet colored line. Now at a later instant, some other particle has come here. Now as that particle is going through this section of this pipe, it'll follow exactly the same trajectory. So there are well-defined constant trajectories through which the fluid elements pass, and those trajectories are what we call streamlines. The geometrical drawing of those trajectories is what we call the streamlines, and hence the motion streamline, hence the name streamline motion. So one way to also think of this in terms of analogy is if you visualize traffic moving in a very ordered way through a path like this, where the cross section of the road or the thickness of the road may not be uniform everywhere. The road may not be straight, so the motion is not necessarily uniform linear motion. But at the same time, the traffic is moving in such a way that the distance between two cars is always remaining the same. And also cars are never crossing lanes. So then they will follow these kind of well-ordered trajectories, which are one following the other, and in such a way that every car passing through a particular point on the road will have the same velocity as the previous car or the next car after that one. So every cross section on the road has a fixed velocity profile. So that would be an equivalent of traffic flow, which is streamlined, as opposed to highly turbulent traffic or random traffic where cars are constantly changing lane, or even extreme cases where there are collisions happening between cars. So they are going through a combination of rotation and translation, or they might undergo rotation after a collision because of angular impulse involved. So streamline motion is the opposite of that. We don't want anything like that. We don't want lanes to change randomly, and we don't want collisions to occur, which will create rotational motion for the fluid elements. We want a very ordered one after the other type of motion where one fluid element is perfectly following the one in front of it, following in terms of path as well as in terms of velocity profile. Okay, so in conclusion, what we can understand is that in steady flow, fluid elements move along fixed and well-defined trajectories. These trajectories are what we call streamlines, such that an element follows the element ahead of it on a streamline with exactly the same trajectory and velocity profile. Okay, so this is the proper definition of a perfect streamline motion. Now, obviously, with most definitions of ideal situations in physics, not all, I mean, very few practical situations will be perfectly ideal. So it's very hard to have a perfectly streamlined motion. But there are many cases where the motion of an nearly ideal fluid or the motion of a real fluid, which can be approximated as an ideal fluid, is nearly streamlined. So it's not exactly that the trajectories will always be fixed. With time, there might be minor variations in trajectory, but they are negligible. And also the velocity profile may not be 100% fixed, but the changes in the or the deviations in the velocity profile over time can be neglected. Whereas in a turbulent motion, it's opposite of this case. There's no way that the velocity profile is fixed. It's very random because of the random collisions. And there's no way that the trajectory is predictable or fixed at all. Because again, it's highly random because of the random collisions. Now, why it's so important to understand this, this whole physical definition of streamline motion, because whatever equations we are going to derive next, the continuity equation and the Bernoulli's equation, the derivation of those equations is completely based on these properties of the streamline motion. The fixed velocity profile, the fixed trajectories, and the part that and the fact that the fluid is ideal, which means that its density is uniform firstly, and that there is no non-conservative force or drag force called viscosity, which is present in the fluid. So these points are essential in being able to execute the derivations which we'll be doing to come up with the Bernoulli's equation and continuity equation. Okay. Whereas the moment these physical properties cannot be adhered to, so that is the motion is no longer streamlined, it's not going to be that predictable. So there's no way we can write pen and paper equations to understand the properties of the fluid as it is in motion. So the moment we're talking about turbulent motion or non-streamlined motion, the mathematics of that becomes much, much more complicated. It cannot be done on pen and paper. It has to be done with some kind of computational simulation. And that comes under the subject of CFD or computational fluid dynamics in engineering. So various branches of engineering, typically branches like mechanical engineering, aerospace engineering, etc. They have quite a lot of application of computational fluid dynamics, which is to do with that more complex process of predicting the motion of a fluid in a situation where it is neither an ideal fluid and nor the motion can be classified as streamlined or steady. Okay, there is turbulence and there is compressibility and there is this thing viscosity involved in the fluid. So in those kind of situations, the prediction model is much, much more complex, and we have to do computer programming simulation of that. And that subject is called computational fluid dynamics. Okay, so that's outside the scope of our 10+2 level syllabus. So that's why in our 10+2 syllabus, fluid dynamics is restricted to one very ideal type of situation, which is nothing but the steady flow or streamlined motion of an ideal fluid. Okay, so having understood all this, now let's come to the two equations that we can derive for steady flow. Okay, so we come to the equations applicable for this particular thing, that is steady flow of an ideal fluid. And we'll see that these are very simple physical principles that we can apply almost logically to the given situation, which is the steady flow. So the first of these is called the continuity equation. So the continuity equation is something like this. Achha, by the way, the trajectories of the fluid elements that we have discussed about earlier, they are only called the streamlines. So over here, this is a diagram of streamlines. These are those fixed trajectories along which the fluid elements are moving. And those trajectories or those paths are called streamlines. Okay. So before we get into this thing, let's understand a few things about streamlines. Streamline is a geometrical construction that we use to understand visually the fluid flow. So streamlines are the trajectories or paths of fluid flow in a steady flow situation. So they are a geometrical representation. Of the flow. Okay. So now, a couple of things to understand about streamlines. Streamlines never cross. We cannot have a situation where the streamlines that we draw are doing this. It is not possible. This is physically wrong. It's not ever happen. Then at any point on a streamline, the direction of the flow velocity is along the tangent. So particularly when we are seeing streamline motion happening through a curved situation where there's a curve in the path. So we'll see that the streamlines also curve accordingly. And as they curve, the direction of velocity vector at any particular point will be given by the tangent drawn to the streamline at that particular point. So if fluid is flowing along these kind of trajectories, then at any particular point, the direction of the volume element's velocity will be a vector along the tangent drawn at that point. And third is something that we'll understand through the continuity equation next only, that the magnitude of velocity of flow is proportional to the number of streamlines per unit area of cross section. Okay. So in simple terms, wherever the streamlines are more loosely packed, okay, the velocity of flow is lesser. And wherever the streamlines are more densely packed, the velocity of flow is more. So if we are going through a narrow region, in the pipeline, so in the narrower part, you can see the streamlines are more densely packed. So in a region like this, the velocity, suppose that is V2, and in a more wider region where the field lines are less densely packed, suppose the velocity is V1. So according to this principle over here, V1 should be less than V2. Wherever the field lines, sorry, not the field lines, wherever the streamlines come closer together, the velocity of flow is more. And wherever the streamlines are drawn further apart, the density of the field lines per unit area of cross section is less. So is the velocity of flow less in magnitude. So these are some important aspects about streamlines itself. Okay. So before we come to the continuity equation and Bernoulli's equation, it's also important to understand this fact about the visual representation or geometrical representation of steady flow. Okay, Kevin, I will just magnify this so that you can see the individual points once. I'm just going through some of your messages. So Ansh has asked about the aeroplane turbulence, the same concept. Yeah, see, turbulence is the same concept when we refer to it in context of aerodynamics also. So basically what happens is a situation like high pressure or thunderstorms or, dense cloud coverage with high velocity winds. It creates turbulent flow of air, and turbulent flow of air interferes with the process of the lift or the thrust force that is generated on the wing of an aircraft through the jet engine or the propeller engine that creates airflow around the wing. So there's a concept called aerofoil. So that aerofoil concept is that if we create airflow in a certain way around a certain kind of shape, which is basically the shape of a typical wing of an aircraft, then because of the difference in airflow above and below the aerofoil, it creates a pressure difference which creates a lift, which is basically the thrust force. So there are various kind of forces that act on an aircraft as it is in motion. So for example, one of the forces is the thrust, which acts in the upward direction, which opposes gravity. So when we wanted to lift up, then the thrust force should be more than the weight of the aircraft. When we want the aircraft to fly at a constant height, then again the airflow around the aerofoil should be controlled in such a way that the thrust or the lift force on the wings exactly balances the weight. There is that. Then, for example, the tail's angle that affects the horizontal direction in which the aircraft is moving as air is flowing, controlling the angle of the rudder or the tail. We can control another component of force, which is a horizontal component of force, which will affect the geographical direction, north, south, east, west, etc., in which the aircraft will be moving. So there are various complex factors like that. But yes, all these factors are controlled with airflow around the body of the aircraft, particularly around the aerofoils, which are those particular shapes, which are like the wings and the tail of the aircraft, etc. So turbulence seriously affects the interaction of this airflow with the aerofoils, and therefore it seriously affects the way the aircraft can be maneuvered in flowing air. Okay, so hope that answers your question, Ansh, little bit about how turbulence becomes significant in aerodynamics. Okay. Then Ayush has asked whether water current flowing is the same thing as velocity of flowing water. Yeah, so sometimes what we refer to as the current velocity, CURRENT, not meaning immediate, but meaning like related to electric current or flow of a liquid. So in this case, flow of a water. So velocity of water flow through a river can also be referred to as the current velocity. That's correct. Okay. Yes, I will take you back to the previous statements also, and I'll scroll down and up both. Okay. Kevin, I hope these two are clear now. So I'll go back up, Snikita, in a moment. Let's go through these points first. Okay. So we have understood that streamlines represent the geometrical understanding or the visual representation of the flow but they are drawn in such a way that they are the actual trajectories along which the fluid elements are moving. And these are fixed, well-defined trajectories. Okay. So now, given the properties that the motion of fluid elements is both irrotational and non-turbulent, so that means the streamlines can never cross each other because there is no turbulence happening. Okay. And the rest is just about kinematics, basically. If you are drawing the trajectory of a stream of particles moving along a particular path, then the direction of the velocity vector at any point of time in that trajectory is nothing but the direction of the tangent. Okay. And now the third point, why the magnitude of velocity is also proportional to the, sorry, it's inversely proportional to, it's not proportional to, so it's inversely, it's proportional to the number of streamlines per unit area. So that means it will become inversely proportional to the area. जहाँ पे area ज़्यादा होगा वहाँ पे density कम है. So if density is less, then the velocity is less. So this statement is okay, that it is proportional to the number of streamlines per unit area of cross section. So in other words, it is inversely proportional to the area. Okay, so hope these points are all clear. Okay, now I'll just scroll up for a moment, catch up on the earlier things that we've written. You will find a more complete description of these kind of theoretical ideas in Resnick Halliday or even your NCRT for that matter. Okay, I've just given you the important points over here, but I've given you the essential points you need to understand so that the derivations we are going to do next are clear to you. Both the continuity equation and the Bernoulli's equation derivation that we're going to do. To understand that derivation, these points should be 100% clear to you. Okay, very good. So now let's come back to continuity equation, main thing we were looking at earlier. So continuity equation is something like this, that if you consider a cross section at one point like this, which is of area A1, and another cross section of area A2 over here, and suppose the velocity of flow at this cross section is V1 and the velocity of flow at this cross section is V2. Okay, now from earlier understanding of streamline motion, we have understood that the velocity of flow at each cross section will be constant. So all through time, any fluid particle passing through this cross section here of area A1 will have this velocity V1. And similarly, at any point of time, any fluid element passing through this one will have a velocity V2. So now if you consider the section in between, okay, so for the section of the pipe between the two cross sections shown. In a time delta t, or you can even write it as delta t, the volume of fluid entering at the first section of area A1. So that delta V is equal to A1 V1 delta T. Now, how we understand this? So let's think of it like this, that I've drawn a somewhat magnified diagram of this. So this is a cross section of area A1. Okay. Now every fluid particle that is coming through this cross section has a velocity V1. Okay. So if we draw a very small volume element like this of thickness ds, okay, so we can see that this ds is equal to v1 dt, where dt is the time taken for a fluid element to go past this section. So what is the volume of this section of fluid? The volume of this section of the fluid is area of cross section into thickness. So it is a1 v1 dt. Okay. So we can generalize this a little and say that in a time delta t, the volume of fluid that is entering through this cross section as a1 over there is equal to a1 v1 delta t. This thing. So now in a similar way, in that same time delta t, the volume of liquid that is coming out of that section, the rate of outflow, that is at the speed v2 and with an area of cross section e2. Okay. So in the same time, the volume exiting the section at the second cross section E2. So that delta V will be equal to minus of E2 V2 delta T. Because at this section you can see this kind of volume of liquid is moving out. Here this kind of volume of liquid was coming in. Okay. Now what should happen is that the net delta V should be 0. Okay, because the fluid is incompressible. So in any section of the pipe, the volume of fluid entering in a certain amount of time must be equal to the volume of fluid exiting at another instant of time. So it is the incompressibility of the fluid, okay, or you can say volume conservation, which says that the net change in volume should be 0. So plus A1 V1 delta T minus A2 V2 delta T should be 0. So that means A1 V1 is equal to A2 V2. This is one way of writing what we call the continuity equation. So since the two cross sections can be selected randomly, okay, or arbitrarily, we can take any two cross sections at any 2 points and write this equation A1 V1 equal to A2 V2 between them. So we can say that this becomes a general equation for any 2 points in a streamline motion. If the cross sectional area at one point is A1 and the cross sectional area at another point in the streamline is A2, then the product of area into velocity at one cross section should be equal to the product of area into velocity in the other cross section. So this is true for all pair of points in a streamline motion. Yeah, and the negative sign is because that volume of liquid is coming out of this section. No? We are considering a section of the pipe between the two cross-sectional areas A1 and A2. So at the cross-sectional area A1, volume of liquid is entering, and at the other one A2, volume of liquid is exiting. Hence the negative sign. Okay, so now the important thing here is, as I told you, that E1 and E2 are cross sections at any two arbitrarily chosen points. That means we can arbitrarily, without any foundation, select any 2 points, and this fact will be true for them. So that means in general we can say that product of area into velocity is uniform. Another for all points in a streamlined flow. Okay, and you will also see that area into velocity is like this. So it is volume rate of flow. So area into velocity is nothing but what we call volume flow rate. That is the volume of liquid flowing through the streamline motion per unit time. So another way of expressing continuity equation in words is that the volume flow rate is uniform throughout the motion. Okay. So at any cross section within the pipeline of flow, the volume per unit time which is flowing through, that is uniform. Okay, so next up, let's understand the implication of this with some examples. So for example, not very surprising at all that if we consider a horizontal pipe of uniform cross section and liquid in streamlined motion across it, then the velocity of flow should be uniform. Okay. The velocity of flow should be uniform, and the streamline should look like parallel lines which are equally dense everywhere. So I'm just doing a basic representation with two streamlines. Okay. So if we consider this cross section here, let's say A0. Cross section here is also A0. So if P1 is equal to V0, then V2 will also be equal to V1. So a horizontal pipe of uniform cross section will have uniform flow velocity. Now, when we say velocity here, we mean magnitude of velocity, V0. It's such that the volume rate of flow, or delta V by delta T, be equal to A0 into V0. But another important thing here is it also means that this also implies that the pressure will be uniform. How I know the pressure will be uniform? That is from a simple consideration that if you visualize a volume element of fluid, okay, as it is going from one section to another, okay, so within this uniform cross-sectional pipe, okay, if we consider a volume element of fluid which is moving. Now consider a cylindrical element of fluid like this which is moving. So it is moving at constant velocity, so its acceleration is zero. So that means the force due to pressure from this side must be balanced by the force due to pressure from this side. So that means, okay, now that same force should act always. So by the time that volume element moves here, it's the same combination of forces acting on its two cross sections. So this acceleration is zero. So that force is nothing but pressure into area. So the net force is zero. So it means that there is same pressure from both sides. And that is true as the fluid element moves from point to point. So that means there's a uniform pressure throughout. So whether we are looking at this point, or we are looking at this point here, or we are looking at this point here, the pressures at all these points will be the same. There will be a uniform pressure. Okay, now as opposed to this, if we take a situation where we have a pipe with a tapering cross section, but still horizontal. And through this we have our streamlines like this. Now the motion could be in either direction, but let's say I'm assuming that the motion is in this direction. Okay. So now compare the velocity of flow at this cross section A1 with the velocity of flow at this cross section A2, you can see that because A2 is less than A1, so B2 has to become greater than B1. This will imply over here that B2 is greater than B1 because A2 is less than A1. Okay. But that will also give me some information about pressure, because now if you visualize a fluid element that is moving like this, some force from this side, some force from this side. Now, as it is moving from here to here, what is happening? It's accelerating. Now, let's say this force has become F3. This force is F4 at this point of time, as it's going through this pipe. So this fluid element is continuously accelerating. So you can see over here that F1 has to be greater than F2. At this point of time, F3 has to be greater than F4. So in general, what we can see that pressure decreases from the point 1 to the point 2, because always the pressure on the left fluid element is more than the pressure on the right hand side. So as we are moving from this point here to this point here, the pressure is decreasing. P1 must be greater than P2. By how much, that Bernoulli's equation will show us, but already you can see by applying simple dynamics and continuity equation, which is nothing but conservation of volume, or the fact that the liquid is incompressible. By just applying these two simple facts, we are able to predict that if fluid is passing through a horizontal pipe in such a way that the velocity is increasing as it's moving from left to right, that means the pressure is decreasing as we are going from left to right. If the velocity profile is such that your speed is increasing from left to right, that means the pressure must be decreasing from left to right. So we can see how pressure variation can be predicted in a horizontal pipe when we look at the velocity profile. Okay, even without the derivation of Bernoulli's equation yet, which gives us the exact numerical value of how pressure changes. Okay, now similarly, if we consider a vertical pipe, and just for simplicity's sake, let's take the cross section of the pipe to be uniform. So here, fluid could be flowing down or it could be flowing up because we are pumping it up, whatever be the case. But continuity equation will tell us that unless there is some turbulence created because of extreme situation, as long as the motion is streamlined, the velocity of flow will be uniform here. Suppose we are being pumping up liquid like this, even in that case, same area, so same velocity at all points. So it has uniform velocity V0 and uniform volume flow rate. Okay. But now that also means that when you consider a volume element of fluid as it is going up at V0, its acceleration is 0. Now, in this case, it's going against its weight. No? So this force has to be greater than this force. Okay. So because its acceleration is 0, F1 has to be greater than F2. So that means pressure is decreasing as you go up. So again, if this point is labeled as point 1 and this point is labeled as point 2, though the velocity of flow will be the same at both the points. V1 is equal to V2 equal to V0. Okay. But P1 will be greater than P2 because they have a vertical displacement. So we can see that even in a uniform cross-sectional pipe in streamline motion, there can be pressure difference created, but provided it is not in a horizontal situation. It should be vertical, or at least it should have a vertical component. If this uniform cross-section pipe had been horizontal, then of course the pressure would have been uniform. So now if we have a tapering or variable cross-sectional area pipe in the vertical direction, then things become even more interesting, okay, because the speed of flow also changes. But of course, there's gravity also to contend with. Okay. So the pressure variation becomes a little bit unpredictable when we just try to analyze it qualitatively like this. Okay, I'll just go back to the last section once more. Not see the messages many of you have. This is the part you were referring to, Amog and Nikita?
Yes, sir.
Okay. So go through this carefully also, why the pressure is changing even though the pipe is horizontal in the second case, whereas in the first case the pressure is uniform. Okay. The uniform cross-sectional pipe, the pressure is uniform, but the tapering pipe, you can see the pressure decreases when we go from the wider section to the narrower section. So the logic of that you can understand. Okay. If water was flowing even in the opposite direction, still the result would have been same, because water flowing from 2 to 1 would have been a decelerated motion. So the force from this side due to pressure must be greater than the force from the right hand side because of pressure. So the pressure must be greater at the point 1 compared to the point 2. Okay, so this is done.
Yes, sir.
Okay. So now let's move on to the second of the maths equations that we can write for streamline motion. It's called the Bernoulli's equation. So this is something that relates pressure with flow velocity v. But when we say velocity, of course, we mean magnitude of velocity. And also the gravitational potential energy concept. So basically, when we consider the height of a section of the pipe with respect to some reference horizontal level. So it is a relation between pressure P, okay, flow speed, we can say, instead of velocity V, and the height H with respect to a reference level. And it is a simple application of work energy kind of concept to understand that. So consider a pipe like this, which has variable cross section and a fluid of density rho, which is in steady flow or streamline motion inside it. Again, the direction of flow is not important. Just for reference, I've shown it like this. So now let's consider a cross-sectional area here, A1, and the velocity of flow or the speed having a magnitude V1. Okay. And cross-sectional area over here, A2, and the speed of flow being V2 over here. And that we have some reference horizontal level like this. With respect to that reference horizontal level, let's say the height of this point, the average height of fluid elements here is H2, and the average height of fluid elements here is H1. Now, next, what we'll do is we'll sort of understand that a volume of liquid that is bounded by these two. So let's say this point is, let's say H, okay, and this point is M. So a volume of fluid bounded by HM at time t equal to t, okay, it moves to a new position, let's say H prime M prime, or let's use some different symbols, QS at t plus delta t. So with it, so in a small time delta t, this cross section has moved here, let's say. So this point is now S, and this cross section has moved here. So this point is now Q. So basically what I'm saying is that this volume of fluid, which was between the points H and M in my first diagram, at time t, it has now become this volume element. I've just drawn it alongside, but it's within the same pipe. So it's become this at t plus delta t. This point is Q, this point is S. Okay. So basically, which is transformed into in that much time. Okay, so on this volume element, okay, if we think of forces which are acting, there's a force from this side, with pressure at that point into area, and there's a force from this side, which is pressure into area. And this force is point of application is having a displacement like this, which is V2 into delta T. And this point of application is having a displacement in this direction, which is V1 into delta T. So to this volume element, or to this volume of fluid, when we apply work energy theorem, we'll say that work done by external forces is equal to change in kinetic energy plus change in gravitational potential energy. So let's start with each of these. So the work done by external force during this time is going to be the work done by these forces, because the other forces that are acting through the walls of the pipe, which are acting normally. They are like normal contact force due to pressure, normal force, which is perpendicular to the direction of flow. So they're not doing any work. But the force that is acting on this face over here, it's acting inwards, and this face is displacing in the outward direction. So you can see that the force which was acting from this side and the force that was acting from this side, one of them is doing negative work, the other is doing positive. So it is minus F2 into S2, you can say, where S2 is this displacement. And this one is S1. So it is plus F1 into S1. So the work done by the external forces on that volume is minus P1A1 into V1 delta T plus P2A2 into V2 delta T. Okay. Now notice that A1 V1 is equal to A2 V2, which is equal to volume flow rate. So we can also write this as P2 minus P1 into delta V, where delta V is A1 V1 delta T. Okay. So just make a note up to this step first. Then we will see the next two terms, the change in kinetic energy and the change in potential energy. So the left-hand side of the equation, which is the work done by the external force on that volume of fluid, as it is moving from time t to t plus delta t, that work done involves the pressure difference. Okay, the pressure difference into this factor. Okay, so that's about the work done side. Now let's understand how we'll calculate the change in kinetic energy and the change in potential energy. Now this is where it becomes very important to understand the concept of the velocity profile. Okay, so once again, if I compare the initial state of that volume element, and if I compare it with the state after some time, so this was my displacement P1 delta T, and this was my displacement V2 delta T. Now once again, if I superimpose these two diagrams, now listen very carefully. Okay, so if I'm calling the mass of liquid that is present over here as delta M1, okay, and it's moving at this instant with V1. If I call the mass of this liquid here as delta M2 and is moving with a velocity V2, okay, now you can see that this is the initial picture at T equal to T, and this is the final picture at T plus delta T. So if we compare these two, now this in between volume that we have, let's say this has some mass M. So this one is basically M plus delta M1. And this one is M plus delta M2. Okay. Now, because the velocity profile is the same, the change in kinetic energy will just become the kinetic energy of the delta M2 part minus the kinetic energy of the delta M1 part. Okay. Because the middle portion's kinetic energy is not changing. It's not that it's the same mass. You have to understand one thing, that a particle which is occupying this position in the first picture, that particle has now moved on somewhere here. Some other particle is coming and occupying that position. But whichever particle is occupying that position, it has the same velocity profile. So the total kinetic energy of all the particles that occupy the middle M portion is the same in the initial and final diagram. So the change in kinetic energy is just the extra kinetic energy of this part in the final diagram minus the extra kinetic energy of this part in the initial diagram. So that's the change in kinetic energy. Now you can see that delta M1 is equal to density into A1 into V1 delta T. So it is nothing but rho into delta V. And delta M2 similarly is density into A2 into V2 delta T. So that is also equal to rho into delta V. So the change in kinetic energy therefore comes out to be half of rho into delta V as a common factor into V2 square minus V1. This is the second term in our work energy equation, the change in kinetic energy. Okay, now likewise, when we are considering the gravitational potential energy, the change in gravitational potential, let's need to consider how the profile has changed from the time t to t plus delta t. So the middle part of the mass, that one's gravitational potential energy has remained the same. But in the final case, it is the gravitational potential energy of that middle part plus the delta m2's potential energy. This is at an average height of h2. And this portion, delta m1, is at an average height of h1. So again, the initial gravitational potential energy is the potential energy of the part m plus the potential energy of the part delta m1. And the final potential energy is this. This is at t equal to t. This is at t plus delta t. So the change in potential energy becomes the potential energy of this section minus the potential energy of delta m1 section. The change in gravitational potential energy is delta m2 gh2 minus delta m1 gh1. And again, in this, remember that delta m1 is equal to delta m2 is equal to density into the amount of volume flowing through in time delta t. So this term becomes like this. So now we have got each of the three terms, okay, in our work energy equation applied to that volume section. So work done equals to change in kinetic energy plus change in gravitational potential energy. So this becomes P1 minus P2 into that volume delta V is equal to this plus this when we put everything together. So this gives us a relationship between the pressure, the speed of flow, and the height with respect to a common reference level. Okay, the comparison of these parameters at two different points, which are selected arbitrarily. So ultimately, it's going to give us a sort of constancy kind of equation, that some relationship between pressure, speed of flow, and height at a particular point is going to be constant for all points within the tube of flow or within the pipeline of flow. So that particular equation is called the Bernoulli's equation. Okay, so this equation finally, if you just keep terms of subscript 1 on the left hand side and subscript 2 on the right hand side, we can see cancelling of delta, we get this kind of a relation. So there's some kind of combination of the physical parameters of pressure, speed of flow, and the height. And that combination remains at all points because we have selected 2 points arbitrarily. So another way of expressing this, that the sum of the pressure half rho v square and rho gh will be a constant for all points in a streamlined flow. This is another way of expressing the same. Okay. So whichever way we choose to express it, this is called Bernoulli's equation. If you notice, each term in Bernoulli's equation has the dimension of energy per unit area. Sorry, energy per unit volume. Very easy to understand for half rho v square and rho gh, but for pressure also, it is like energy per unit volume because pressure is force per unit area. So it's like force into displacement per unit volume. So each of these terms have the dimensions of energy per unit volume. You can think of them like energy density terms. Okay. So also they are called, each term is called a head. So the term P is what we refer to as the pressure head in the Bernoulli equation. Half rho v square is what we call the kinetic head. It's like kinetic energy per unit volume, and rho gh is equal to what we call the gravity head. So the sum of the three heads should remain constant. Now, with this extra knowledge in mind, if you think of the three examples that we saw for pressure variation previously, you'll see how they make even more sense now with the Bernoulli's equation in place. Okay, if you compare on a horizontal pipe of uniform cross section, what is happening is that at these 2 points, the kinetic heads are same. Okay, the gravity heads are anyway the same because they are at the same height. So P1 must be equal to P2. But for example, if you consider the vertical pipe but of uniform cross section, whether you consider the liquid going up or coming down, whichever be the case, you see that because there's a height difference between these two. So at the point 1, the gravity head is greater than at the point 2. So at the point 1, the pressure head should be less than, because H1 is greater than H2. Okay, and not only that, we'll find a numerical in this pressure difference also by applying Bernoulli's equation. Similarly, if you take the tapering pipe, so continuity equation is telling you that as you go from this point, let's say point number 1 to this point, point number 2, the kinetic head at point number 2 is greater than this. So immediately the pressure head has to be less because the gravity head is the same. So in terms of just comparison, is giving you the same information that we had got logically by applying continuity equation, okay, and the concept of free body diagram to a moving fluid element. But now it will also give us an additional way of calculation of this pressure difference, because in deriving Bernoulli's equation, we have essentially applied work energy theorem. So we apply work energy theorem here through Bernoulli's equation by the statement of Bernoulli's equation. You'll see that if I know V1 and V2, for example, or if I know A1, A2 and the volume rate of flow, then I can find out the pressure difference between these 2 points. Okay, so we'll conclude here today, people. In the next lecture, we will look at applications of Bernoulli's equation, which will not take too much time. Okay, so hydrodynamics should be completed in the next lecture, and maybe we'll set aside some time for more doubts and questions from So next week we will be looking to wind up fluid mechanics and start with the next section, which will be properties of matter. So properties of matter will start with properties of solids, namely elasticity. So we'll see Hooke's law in elasticity and the various moduli of elasticity you might have heard about: Young's modulus, modulus of rigidity, and Bulk's modulus, etc. So we'll be looking at those particular aspects of properties of matter. Okay, so that's it for today's session, people. Wish you all the best and thanks for attending.
Thank you, sir.
Okay, you can now go ahead and please try and complete the question set from H.C. Verma's chapter in fluid mechanics, okay, including the hydrodynamics one, because they are direct application of these formulae.